In this video, we continue with chapter 4.8, and we'll be looking at examples of conic sections and how we can use the change of basis that we learned in chapter 4.7 to rotate conic section equations. So every conic section in the xy plane has an equation that we can write out in this form. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where a through f are constants and some of them may well be zeros. So identifying the graph of this equation is fairly simple as long as b, the coefficient in the xy term, is 0. So when b is 0, the conic axes are parallel to the coordinate axes, and the identification is accomplished by writing the equation in standard form, which we get to by completing the square. So they call it standard / completed the square form. The standard forms of the equations of the 4 basic conics are going to be given in the summary following on the next pages. So for circles, ellipses, and hyperbolas, we think about this point HK as the center, and you saw that same notation back in calculus class. And then for parabolas, HK is a vertex, which I believe you also saw that same notation back in calculus class. So here's the standard forms of equations of conics. For a circle, we've got x minus h squared plus y minus k squared equals r squared. We're used to looking at the circle centered at 0, 0, which is then just x squared plus y squared equals r squared when we're centered at the origin. But if you shift the point, remember HK is the center. And then in the ellipse, we call 2 alpha the major axis length here, and 2 beta the minor axis length here. So here's my ellipses. If you've got an ellipse that is stretched out more along the x-axis, then 2 alpha is the major axis length. And if you've got an ellipse like in the second picture stretched out more along the y-axis, then 2 alpha is labeled along the y-axis because that's now the major axis. So the major axis is wherever you've got more of a stretch factor. And ellipses are centered at HK also. So if your major axis is the x-axis, your function looks like this, with the x minus h squared over the alpha squared. And then the y minus k squared is over the beta squared because y is the minor axis in this scenario. In the second scenario, where y is the major axis, then the y minus k squared is over the alpha squared. And in an ellipse, this equation equals 1. So in a hyperbola, we talk about 2 alpha being the transverse axis length and 2 beta being the conjugate axis length. So in the first diagram, the transverse axis corresponds with the x direction, and the conjugate axis corresponds with the y direction. So we label those 2 alpha and 2 beta. And then the big difference between the hyperbola and the ellipse equations is the ellipse had addition in the center, and the hyperbola has subtraction between the terms. The hyperbolas are also equal to 1. And then over here in the second picture, we still have subtraction, but we see the transverse axis now is the y-axis when the parabolas kind of open up and open down as opposed to opening sideways like in the first picture. And the conjugate axis is the 2 beta length, which corresponds with the x's there. A parabola has this complicated form in general. X minus h squared equals 4p times y minus k, where the p is the distance from the vertex to the focus. We're more used to seeing parabolas in y equals form with the quadratic look. So if you expand this out and combine terms, you get a quadratic looking function there. And so this first diagram is what we're used to seeing as parabolas, where y is a function of x. The second picture is where now x is a function of y, and we're looking at what doesn't meet our usual definition of a function anymore because we don't pass the vertical line test there. So this format is x and y just reversed in terms of variables. So You might not have seen these sideways parabolas very much in algebra class, but they do exist. We're just now thinking of y, x as a function of y. And maybe you did some of these when you did rotations back in calculus. If you remember back to rotating like the donut or washer rotation methods, I think you did some calculations like this where you can integrate in terms of x or y depending on your reference point. Okay, we're going to look now at example 5 from our text. It's about identifying conic sections. So the standard form is the first move we always make. So here's our function x squared minus 2x plus 4y minus 3 equals 0. So we have to complete the square and put that into standard form. So that's this equation right here. X squared minus 1 all x minus 1 all squared equals 4 times negative 1 times y minus 1. So the graph of this equation is a parabola with the vertex at hk equals 1, 1. The axis of the parabola is going to be vertical, and the directed distance p from the vertex to the focus is p equals negative 1. So you can see that in the way that we've got the factored form here. Here's our p right here. And for the other values, if you're not sure, come back and look at the parabola equations over here. So you can see we are in our usual familiar open up parabola format. Here's our p equals negative 1. That's the distance from the vertex to the focus. And so the focus point is going to be at 1, 0. And finally, the focus lies below the vertex, so the parabola opens downward. So here's a diagram. The diagram is worth 1,000 words because you can visualize, okay, there's our focus at 1, 0, our vertex at 1, 1. This is an open down parabola. And then in the second example, we look at a function that is an ellipse. So here we've got x squared plus 4y squared plus 6x minus 8y plus 9 equals 0. And we put that in standard form. And now in standard form, we can see it's in the format of an ellipse with the addition in between the terms. And the center is at negative 3 and 1. That's our h and k. So you can see this diagram down here. You can see that the major axis is the x-axis or the horizontal axis, and its length is 4. So we say 2 alpha equals 4. The length of the minor axis is 2 beta, which is 2. So we're going to say beta is 1. And the vertices of this ellipse occur at negative 5, 1 and negative 1, 1. And the endpoints of the minor axis occur at negative 3, 2 and negative 3, 0. So those points are all labeled in our diagram here. So note that neither of these conics have xy terms in their expansions. So we've got the expansion circled in red up here and the expansion circled in green here in part B. Notice neither conic has an xy term. So the degrees of the graphs of these conics are, the axes of the graphs of these conics are parallel to the coordinate axes. For second degree equations that do have an xy term, the axes of the graphs of the corresponding conics are not parallel to the coordinate axis. So in such cases, it's helpful to rotate the standard axes to form new axes that we call x prime and y prime. So this is where our change of basis techniques are going to come in. The required rotation angle theta is measured counterclockwise, and we can find it using this equation: cotangent of 2 theta equals a minus c all divided by b. And so then we'll be in our standard basis for R2. B is 1, 0, and 0, 1. That's going to rotate to form this new basis, which is b prime cosine theta sine theta in the first vector, and then negative sine theta cosine theta in the second vector. And you can visualize that here below. So you can see the cosine and the sine in the rotation from 1, 0. That rotates to cosine theta sine theta in the first quadrant. And then the 0, 1 point from the y-axis rotates to negative sine theta cosine theta in the second quadrant. So let's look at a couple examples of how we calculate the angles of rotation for conics. So this first diagram here gives us conic A, it's an ellipse. And here's the equation for conic A. So if we go back to our definitions of conics, remember that original form is, see, I'll write it up here, ax squared plus bxy plus cy squared plus dx plus ey, I'm gonna run out of room, plus f equals 0. So I've trailed down here to the next line. And so in this conic, we've got x squared. So we'll say a is 1 and ignore the fact that we've got capital A here instead of lowercase a. It's the same coefficient we're talking about. We've got a minus xy, so b is -1. And then we've got a y squared, so c is 3. So this graph's an ellipse. So to figure out that that angle of rotation, we use the cotangent of 2 theta equals our formula here, a minus c over b. So we just plug in our values from the coefficients of the equation. So 1 minus 3 over -1 gives us a -2 over -1, or +2. And so cotangent of 2 theta equals 2. So working backwards with inverse cotangent and division, we get theta equals 13.28. So that's how much this was rotated. And this is in degrees. But you could do the same kind of calculations in radians as well if you preferred. Okay, now let's look at conic B. That is a hyperbola. And so it's rotated. It looks like it's a hyperbola where the horizontal is a transverse axis and it's rotated this way since we rotate counterclockwise. So let's take a look at our values here. We've got A is going to be -2, B is 3, and C is 2. So when we plug those values in, the calculation here is -2 minus 2 over 3. So that's where this -4 over 3 is coming for. And so cotangent of 2 theta equals -4/3. And then using our inverse cotangent and division, we get theta equals -18.43 degrees. So this one actually might have rotated in the negative direction. So it went this way. So it started out with the transverse length, the x-axis, and then it kind of got knocked to the clockwise direction. So by default, we would go counterclockwise, but since we've gone the other direction, that's why we've got this negative angle of rotation here. So if you want to go clockwise, think about that as a negative angle of rotation. Let's take a look at example 6 from our text. So here we're going to see how to come up with a transition matrix for rotation in R2. So we want to find the coordinates of a point x, y, and R2 relative to this basis where b prime is cosine theta sine theta for the first vector and then negative sine theta cosine theta for the second vector. This is that new basis that we saw in the diagram back here. So we see how you're rotating from 1, 0 to cosine theta sine theta, and from 0, 1 to negative sine theta cosine theta in the second quadrant. So by theorem 4.21, back when we saw in section 4.7 how to change the bases, we can put into a matrix together b prime and b as column vectors. So the cosine theta sine theta and negative sine theta cosine theta from b prime are here as column vectors, and then b, remember, is the standard basis 1, 0 and 0, 1. So those values are the third and fourth columns in our matrix. Okay, so B is the standard basis. So P inverse is just going to be represented by B prime inverse because we don't have to reduce this to get the identity matrix out. So you can use the formula for the inverse of a 2x2 matrix to find B prime inverse. So that's right here, the cosine theta, sine theta, negative sine theta, and cosine theta. So because this is sine and cosine, we go through our 2x2 matrix inverse. We saw that back in chapter 2. You did a lot of work with that. So it's the 1 over the determinant multiplied by the swappings and the negatives swapped in there. So that's how we got this cosine theta, sine theta, negative sine theta, and cosine theta for the inverse of the transition matrix, P inverse here. And so we're going to let x prime and y prime be the coordinates of xy relative to B. Then you can use the transition matrix P inverse to find x prime and y prime. So you would put in your xy values and multiply that by this P inverse transition matrix. For generic x and y, you're going to end up with this formula down here where x prime equals x cosine theta plus y sine theta, and y prime equals negative x sine theta plus y cosine theta. So you can see if you do that multiplication out, that's how you get this equality. Okay, so the general second degree equation for our conic sections here, set equal to 0, can be written in this form: a prime x prime squared plus c prime y prime squared plus d prime x prime, and e plus e prime y prime plus f prime, where f prime is a constant, and a prime through f prime, in fact, are all constants, where our x prime and our y prime are this new rotated coordinate system. And it can be written in this form by rotating the coordinate axes counterclockwise through the angle theta, where we find theta using this formula: cotangent of 2 theta equals a minus c over b from the original second degree equation for the conic section. And then the coefficients are obtained through this formula we just saw, where x is x prime cosine theta minus y prime sine theta, and y equals x prime sine theta plus y prime cosine theta. So let's take a look at how the proof of this works, and then we'll look at an example. So here's kind of an overview of the proof. You can pause and read through it more slowly if you want to go more in depth. So here's our proof that a rotation is going to eliminate the xy term from the equation, because notice our format here, now we've lost the xy term. And that's the form that we saw the original conic sections in without the xy term. So you let theta be a solution to cotangent 2 theta equals a minus c over b. And then you substitute in here our x and y values in terms of x prime and y prime into the equation, the original conic equation. And then to show that the x term is eliminated, you analyze the first 3 terms here. So if we substitute in our values here, a prime times our x substitution squared, and then plus b prime, or b times the x substitution with x prime cosine theta minus y prime sine theta, multiplied by the y substitution, which is x prime sine theta plus y prime cosine theta, and then plus c with the y substitution squared. So that's x prime sine theta plus y prime cosine theta all squared. When you expand that out, you end up with these new terms. And you can see those simplify to be negative x prime y prime multiplied by a minus c times sine 2 theta minus b times cosine 2 theta. But we know that cotangent of 2 theta is just cosine of 2 theta over sine 2 theta, which is a minus c over b. So you can see, okay, well then that implies that b cosine 2 theta equals a minus c quantity times sine 2 theta. And so that shows us that the coefficient is 0 here. So that's how you can see the new xy term here gets 0 for its coefficient. So let's look at an example. We're going to rotate axes to eliminate the xy term from this function right here. 2x squared minus 3xy minus 2y squared plus 10 equals 0. So the first step is to find the rotation angle theta. So we identify A is 2, B is -3, and C is -2. So that's going to give us +4 on top and a -3 on bottom. So we get -4/3. And then working backwards, we can find that theta is 71.57 degrees. So sine of theta equals 3/√10, and cosine of theta equals 1/√10. And then we can substitute in using our formulas for x and y, using what we know about sine and cosine here. And so we plug those into the original equation here. 2x squared minus 3xy minus 2y squared plus 10 equals 0. And then when we simplify, you lose the xy term and you get this equation here. X prime squared over 4 minus y prime squared over 4 equals 1. That's the equation for a hyperbola, and the transverse axis is along the x prime axis. So you can see how we are able to use our change of basis knowledge here to rotate the axes and rewrite our hyperbolas or other conic sections without the xy term. So we'll be doing some practice with this and using change of basis in the group problems.